Hi everyone, I would like to introduce this session, another part of the application of AI in land cover classification and clustering. And the next one should be the neural network, um, a new classification, and how I would like to introduce about the concept of neural network and how um, neural network can be used for land cover classification. First of all, I would like to introduce about the uh, concept of neural network. The neural network started from our motivation of creating an electric brain. Um, Before that, we could look at the biological brain, where our brain uses extremely large interconnected network of neurons uh, for the information processing, and to model the world around us. Simply put, a neuron collect an input from other neurons using dendrites, and the neuron sums all the input, and if the resulting value is greater than a threshold, it fires. The fire signal then sent to another connected neurons through the axon. So we, with the motivation of creating electronic brain, we create something like a perceptron, what we call, it's similar to the neuron in a biological brain. The perceptron developed between 1950 or 1960 by a scientist called Frank Rothenberg, and inspired by early work by the Warren McCulloch and Walter Spitz. But today we use another models for artificial neurons, but we still follow the concept of the principle set by the perceptron. Um, when you look at the picture, you look at the picture and you see that the concept of perceptron, the perceptron receives uh, many different inputs, node, called input node, and they connect it with a neuron that we call, and the connection have weights for each connection. So uh, at this neuron, we do sum of the weight um, of all the inputs, and we have a z value as sum of the all weighted input, and is this then by a matrix, and then after that we use some activation function called y. The y change the value of this sum, and it make an output of the perceptron. So in the short form, you can see that we have an input layer, have an input neuron, and we forward the value of the input into a neuron, uh, what you call here, with the concept of a sum function, and also a function that change the value of the sum. Um, Based on this concept of perceptron, we the people develop a kind of multi-perceptual uh, and we call feed-forward neural net. I would like to introduce afterward. So the input vector from training set are presented to the perceptron. Uh, One after another weight are modified according to the following equation. Uh, for an input I, the weight of I is the weight plus with A star, and G is the sum of all input uh, multiple with TA and multiple with P and I, where Z is the kind of the what you call the activation function, and A is what you call the learning rate. I would like to explain about the learning rate later on. And after a lot of known input put to the perception, we can do you can correct, and you can find the right weight for the network of the perception, and that is a process of what we call training. And after training, we have a kind of a network with the fixed weight for each connection from one uh, perception to the other perception, or what we call one neuron to the other uh, neuron. So what is a perceptual doing? With suppose that we have a two input. So we call the value of input is the weight one multiple with the input one, and weight two plus with weight two multiple with input two is t value, and t is the output after some t is the kind of threshold, and if we do the output, and we compare, and we do something like for classification, we do something like we assign the output value is 0 if this sum is smaller than the threshold, or assign it value 1 if this sum is larger than the threshold. We have a look a bit on the what we call activation function, the function that changes the sum value and to make the output for the perception. Um, we have different kind of activation function. The first one may be used is step function. The step function, activation function, will put value uh, a if the if y larger than bigger than the threshold, or the value of a is would be 1 if the y is bigger than perceptual, or larger than and larger than 0. So we did this step function. We would like to see that the step function, like put all value to 0 and then 1 for another value. This activation function, step function, have some drawback. Suppose that we're creating a binary classifier. Sometimes we should say that yes or no, activate or not activate. But the step function do not could do that for you. But in case we have some value between 1 and 0, it doesn't work. For example, in this case. So we have another function we call linear function. The function formula is a equal to c and x. It's a kind of straight line function where activation is a proportion of the input, and based on the weight sum of the value, the input from the neuron. In this way, it gives a range of activation. So it's not a binary function. We can definitely connect a few neurons together if more than one file, and we could take a max and decide based on that. So it's okay too, but they have a problem. The problem is that derivative with respect to x and c. That means the gradient have no relationship with x. So the constant gradient and distance is going um, to to be the constant gradient, and there is an error in prediction. The chain of bifurcation is constant and not depend on the chain. Another the most popular and the most used uh, activation function is the sigmoid function. Uh, The sigmoid function is based on this formula, and the comparing with the other function, the sigmoid function looks smooth, and it's like a step function, but it's not really like that because it produces value between the zero, between -1 to 1. So it can produce some value between 0 and 1. It's quite flexible. Another function is called tank function. Uh, the tank function produce value between, as I said before, it produce value between 1 or -1. Yeah. And we have another function we call ReLU function. This ReLU function is formula is x is max of 0 and x. Between so this function is the non-zero, it's the positive function, and always the value put at 0 and the thing above the 0 would be linear to the output value. So the output value is always positive. The ReLU function is used in a lot of deep learning model I would like to introduce afterward. So we can now I said about the combining perceptron into a kind of network. We design the network into the layer. We have designed that network into the layer. The first layer is input layer that receive the input value for example, the vector, for example, one vector, for example, and the input layer forward the value into the hidden layer, the layer in the middle. The hidden layer maybe there's not only one hidden layer, but there's a lot of might be some hidden layer, and the more hidden layer out there, it should be we call the deeper the network is. So the chaining process is a kind of train the network to understand to understand the characteristics of the network based on what we have on the training data. So we put the training data and teach the network and let the network learn how to classify or how to do regression. This network what called feed forward, this feed only in one direction, and it doesn't re recurse back the value. So the value is also put forward from the input to the hidden layers, and from the hidden layer to the other hidden layer maybe, or to put directly to the output. It's very for the ordinary neural network. It is very popular that we have we made a lot of 3 layers with one input, one hidden, and one output. The process of training the network, um, the process of training the network is in for this kind of neural network because we usually use kind of backpropagation training. The backpropagation is a common method of training a neural network. This network set a goal for backpropagation is to optimize the weight so that the neural network can learn how to correctly map the arbitrary input to the output. To tune the neural network between the hidden layers and the input layer, we need to know the error of the hidden layer. Um, we know the error at only output layer, and we know correct the output based on training sample, and we already know the output predicted by the network. So the network will suspect that to take the error that the output layer and proportionally propagate them backward to the hidden layer and then to the output layer. Yeah, so we can change the weight of um, doing the change of the weight, we use the gradient descent error minimization algorithm. The perceptual learning rule is an algorithm that adjusts network weights to minimize the difference between actual output, out G, and the target output, tag GPG, and we can qualify this difference defining some square error function. The sum over the output G of the data point G and the training pattern P. So we based on the E as the we call the loss function. We based on this error, we distribute the chain in for each weight value of W ij, and then uh, we do output. So describe this back propagation. We can describe that like first at first we set an arbitrary, or we set a value for the weight of the neural network, and then from this start we can we do input for like a training sample. We do one input training sample, and of course because the network doesn't know how to do the right thing, so it produce some error. It produce the wrong value of the output. So we compare, because in training data we know already the output, so we can compare the known output with the produce the predict output by the network at that current state. And then based on that two value, we do have something like error of the output. And based on that error, we use the gradient descent algorithm to uh, propagate back the value and to change the weight of the value of the network of each connection uh, between the neuron in the network back to the hidden layer, and from the hidden layer back to the input layer. For example, if you have a tree, or if you have a more deeper neural network, the gradient descent and the change would be from the output to the first the, the the connect hidden layer, and to the other hidden layer, and to the final hidden layer, and back to the input. So the gradient descent is based on derivative of the error We have error as a function of the weight, and we do derivative of the error function um, to each weight, and then we have a kind of like the derivative function. We can calculate that derivative function based on the error value, and we do some like for example we do like we change the value of weight. For example, weight 1 for the after training of the sample at the point t is changed by neta multiple by the derivative, the value uh, calculated um, by the error that by the error, and then neta. is a kind of what you call the learning rate. The learning rate decides how quick and how how the step jump uh, of the chain value, and it decides also the thing like the conversion of the network. So after many training and many chain, the network, the weight of the network um, at some point doesn't change anymore, or the changing is very little. So when the changing is little under a threshold, we can stop the training of the network. And of course, at that point, we still have some error. But the error, the total error, or what we call the loss function, um, it calculates based on the error, is a minimi or is set at a local minimum or a global minimum. We accept that value, and at that point, the network is trained and can use the network to classify. For example, you look at this picture, you can see that maybe at the point T of training, we put an input sample, and it produces the value like this. But the actual value we know is like this. This one is for classification. So we have an error based on this one. For example, we do some, like calculate the error for the first output node, the second output node, third output node, and the fourth output node, and we sum this error and do square power of this error, and then sum of that to make a kind of the loss function, and we try to use that short loss function to calculate the derivative value of this loss function to each wedge of the connection, and then like we change the wedge like using this formula. And the conversion of, as I said before, the conversion of the network is based on the data value. Is the kind of like a learning rate, what you call. So you understand already the principle, the concept of the neural network, and we'll know how to use this neural network for land cover classification. For example, you already know that for the land cover classification, we have some training data that we have like gray values of the spectral bands to create a kind of vector, and the vector is of the gray values of each spectral band is a kind of input, and we do that input, and we have in the training sample we use the output. The output is the training is the label of the land cover class of each known pixel. So we can, from that we can have the output as the land cover class. For example, if the land cover class each output node is a present a land cover class. For example, the red one is the and the green one and the blue one. The red one represent for construction land. The green one represent for forest, or the blue one represent for water, for example. So the value, the output value here, if the water, if the training data is the water, we do the input for the real value of spectral band, and we have output as we know already is water. And of course at the start of the neural network, it doesn't predict that it's water. It predicts someone maybe the water, or maybe the construction land or the forest. So we have to change the network to change the to let the network change their weight So and then after training, a lot of training, we have a network ready for classification. And the hidden layer depend on depend on the case. Um, the depth of the network depend on the case, but mostly with the ordinary remote sensing data. uh, and for the classification, we use one hidden layer is enough. So we do the input already, the green numbers of the spectral band. For example, for the Landsat, we have 7 band. We have a yeah, the input vector have three um, members, three values. Um, Landsat, we have 7 band. We have 7 values. So the input is 7 node, and then we have hidden layers, and output layer maybe it's a land cover level. It's the principle of that is not different from the other. But in this case of classification, we should define something like a fixed value of 0, 0, 1, or 1, 0, 0, or 0, 1, 0. Um, we have something like maybe we can do something like a kind of regression to create a kind of what we call soft classification with this neural network. In this case, we accept every value of the output. For example, it's not 0, 0, 1. It's not fixed like that. It's a hard classification. The soft classification is something like uh, 0.3 of construction land, 0.2 of forest land, and 0.5 of water. So it's quite flexible with this neural network. And that's what I would like to introduce about the concept of how to use neural network for land cover classification and the concept of neural network. And I hope that you can got the very basic information on how to use the neural network for doing land cover classification. Thank you.